Okay, let me try. Okay, so because of typhoon, so yeah, so another student you not come today, so we need to make a movie for him.
Okay.
But so today we are one-on-one, one-to-one, okay?
Yeah.
So you can just ask me question anytime. Okay, so let's have a simple review for next week material. Just stop me anytime when you have question. If you feel I don't know, then you ask me question.
Okay.
Okay. Okay, so next week, I think we stop here in this slides, yeah, to show you the 3D structure of the probability density, which means what's the chance the electron may show in different orbits. If you have ever taken the fundamental chemistry or fundamental physics, you know that we have something called periodic table, something like hydrogen, right? Helium, lithium, right? So they have different Z number. Z is atomic number. So when they have different atomic number, also means they have different electron number. So if you have only one electron, you put in 1s orbit. Second electron also in the 1s orbit. Then the third electron will be in the 2s, then 2p, 2p, then 2s, right? Okay, so this is like the periodic table. Okay, so do you have the slides? Okay, yeah.
I think you need to change the positions.
Oh, really? Thank you. But it's okay. Yeah, I cannot do anything better. Okay. Okay, maybe here. Anyway. Okay. Yeah. And then let's go back to see how do we generate this. Okay. Yeah. Remember we talked about what's the Bohr model, right? Bohr model have some limitation. So what's the Bohr model? So this is the Bohr model. Bohr model means the nucleus is in the middle, right? Positive charge. All electron negative charge. They have some fixed orbit, just like the sun and the earth. All the electron is like the planet surrounding the sun, and right? But in fact, this may not be correct because we have such limitation, okay, for Bohr model, and after we use the Schrödinger equation, we feel like electron is not in the orbit. Electron is somewhere here, somewhere here. They are jump from here or there, and we call it quantum leap. Quantum leap means when electron, they are not moving. They are sometimes here, sometimes here. So they don't have velocity, and they don't have the emission of the EM wave because they are not moving. They are jumping. Okay. And also, all this problem we will explain this later. Okay. And we know that this is the classical dynamic. So if I have a wave, you learn this maybe in your high school or in the fundamental physics. Then we can write it like this format. And this format also equal to this. So this is what we call the Euler equation. The Euler formula or Euler equation, okay? Euler equation can put exponential and the pi together. So exponential I theta equal to cosine theta plus I sin theta. So exponential minus I omega t minus x over v. This can be rewritten like this. And these are sine cosine, they are periodic function. So which means they will come up and down, up and down, up and down. Okay? So the period, okay, and I think the period equal to 1 over no, not 1 over, so we know that if we have a period t multiply the frequency will equal to velocity. Okay, so this v is velocity. Also, we know that 2 pi frequency equal to omega. It is this omega. Okay. So this is the periodic function. Okay. And from all this, we say E equal to h mu. Sorry, this mu is the frequency. Okay. Mu and v, they are different. V is the velocity. Mu is frequency. Okay. And the mu equal to 1 over f. Okay. In fact, this is mu. Okay, this is mu. And okay, so let me rewrite this. We call this lambda. Okay, and this is mu equal to v. Lambda times mu equal to v. Okay, so here is lambda, here is mu. Okay. Then after this, the a e minus 2 pi vt minus x lambda can be rewritten as this one. Okay. And if we derive 2 times by the location of displacement, 1 times with the time, then this will be our Schrödinger equation. You learn this the first half, first 8 weeks from Professor Du, right? Yeah. And this is, so when you do this in last few weeks, you do it in 1 dimension, means only x and time, right? So in order to put it inside the hydrogen atom, hydrogen have 1 proton in the center and 1 electron outside, right? In order to make a 3-dimensional, we need to rewrite it not only x, y, and z. This is the 3-dimensional, time dependent, means you have location and you have time. Okay, but we want to separate the location and time to make a time independent equation. Okay, so they look totally the same. Okay, this is the time dependent formula. This is the time independent formula. They are all the same. The only difference is this is lowercase. This is uppercase. The difference from lowercase and uppercase is the time. Okay, we say the uppercase side equal to lowercase side times the time. This is the function of time. And here, no time. So we call this time independent.
Okay.
Time independent shifting equation. This is time independent. This is time dependent. And because this is time independent, we also call it steady state form. Steady means not time independent. So no matter how time changes, they are the same. Steady. Okay, so this is one dimensional. This is three dimensional. Okay, three dimensional. Okay. And it's not good. It's not good to write. It's not good to write the equation in x, y, z because we have one positive ion in the center, negative ion outside, right? So we should use the spherical coordinate, not the Cartesian coordinate. Do you know what is Cartesian? It's x, y, z is a Cartesian. So this is spherical. Okay. Okay. So spherical we have r, theta, and phi. R is the distance to the center. We call it radius. Theta we call it zenith angle. It's the angle between the z to the vector.
Okay.
And phi is the projection of the vector and the angle between the x to the projection.
Yeah.
This is the zenith, the azimuth angle. Okay. And if we not use the x, y, z, if we use the r, theta, phi, we know that Laplace this delta square. If it's in Cartesian, Laplacian equal to partial x squared partial y squared partial z squared partial equal to this one. But in the r theta phi, if I want to get what is Laplace equal to delta dot delta. So we can use these two functions to derive this. We try this next week, right?
Okay.
So the Laplace in the spherical coordinate will become this. Okay?
Okay.
And we need to solve this. If we want to solve this, I want to first let's know phi. For this one, no phi, okay? Phi, no phi. So we need to do something we call it separation of variable, okay? So we define psi equal to r theta phi. Phi is a phi function, theta is a theta function, r is a r function. We know the result already, right? This is the result. This is the result, okay? So you can see psi equal to r multiply theta multiply phi. This one multiply this one multiply this one. Oh, sorry. This one multiply equal to this. Okay?
Okay.
So you can see in R, the only variable is R. There's no theta, no phi. In here, we have only theta. Right?
Okay.
No R, no phi. In here, we have only phi. Right? No R, no theta. So phi is a phi only function. Theta is a theta only function. R is a R only function.
Separation. Right?
Separation, yeah.
Okay.
Okay, so this is mathematics, okay? So we separate. This is a phi only function. No R, no theta. Here is the R theta only function. No phi. If a function, no theta, no R, no phi, because equal, right? So they equal to something. This thing is independent to phi, independent to R and the theta. So this thing is a constant. So it will be a constant, okay? So we say this constant, we name it ML2, okay? Then we can get, this is the function of phi. So phi will be A, this is the magnitude, and the exponential. Remember what is exponential? You become cosine and sine. Right? From the Euler function, exponential I ML phi will become a combination of cosine phi and the sine phi. Right? So this is why we look at this. Okay. So this means cosine sine phi, cosine sine phi, cosine. So they are all E, I, C, I phi, right? So this is the solution. INL phi. INL, so ML equal to 1, then 1 phi. ML equal to 2, then 2 phi. Right? So this is the ML quantum number. Later we'll explain what is ML, what is orbit. And the final one is the principal quantum number. You learned this before, right? When you do the one-dimensional Schrödinger equation, when you run the last example with the Professor Du, right? At that time, because it's one-dimensional, the potential wave, so you have only one quantum number, which is the principal quantum number. So inside a potential wave, you have different state. Different state present what? Different energy. Okay, so this is principal quantum number, indicate the energy of the electrons. Okay, this one is for orbit momentum, and this one is for magnetic energy. I'll explain this later. Okay. So we also can solve, this is to solve R and the theta. Okay. So we separate the R and theta. This is, we call it another constant called L times L plus 1. And why? You don't need to know why, because if you have learned something called Lagrange equation, okay, Lagrange equation. So this is not important, okay, I just want to tell you why, okay. Lagrange, I don't know how to spell. Okay, Lagrange. Your network is not good. Okay, so there are a kind of spatial equation we know how to solve. If they have this L times L plus 1, then we know how to solve it. Okay, so that's why we call this constant L times L plus 1. Okay? So if this is L times L plus 1, we know how to solve it. Okay? Okay, so finally, we have some solution like this. This is our solution. Okay, so we have this for the energy, this for the orbital momentum, this for the magnetic energy. And then we will try some example to make you more understand about all these numbers. Okay?
Okay.
Try some example. And next week we try this example, right? Okay, remember we say in your final you can bring some cheat sheet, one A4 paper, write down whatever you want. Okay?
Okay.
Okay, and also you need to bring the calculator. Okay, calculator. Okay. So what is a calculator? Calculator is this. Okay, because you may have some very strange number need to calculate. So for final exam, also bring the calculator. Okay. And the cheat sheet means final we can bring one page A4 paper and write down whatever you want. Okay, you can write some formula, you can write some example or whatever with you. Prepare your own. It's just like a reference because I may not give you the equation or whatever. You need to have some only one page.
Oh, only one page.
Okay, well, so in your final, one page and the calculator. Okay. So we try this example last week, right? So from not here. From this table, we can get this is the R100, right? Means this means this is the Schrödinger formula for the n equal to 1, L equal to 0, ml equal to 0. And then we want to find the energy for this orbit. Okay?
Okay.
And this is the equation. Also, this is the Schrödinger equation we just derived from here. So we have these two clues. Okay. This is 100. This is the Schrödinger equation. Okay. We put these two things together. So we need to get the dr squared dr. And this is R. Okay? So what is the differential the derivative of the R10? This is dr is this one. And then multiply R squared, then dr again. It becomes this one. And we can put this into this formula. Okay, put this into this, and we can get this. Okay, something plus another thing equal to 0. So it means this has to be 0 and this has to be 0. Okay, both need to be 0. Okay, because total is 0. So this is 0, this is 0. Okay. And then let's get all this and A naught equal to this number. Let's try to put all the number in Excel and to try can we get this number. Okay. Excel. Okay, we want to get 4 pi epsilon 0. So what's the epsilon 0? We last time physics constant. Okay. Where is the constant? Okay, so what is epsilon? Epsilon here, 8.85 times 10 to the minus 12. Okay. 8.85. 8.85 times 10 to the minus 12. Okay. And what else? Pi, what is pi? Pi is pi. Okay. Wait. Pi. Okay. Planck constant divided by 2 pi. Okay. And what is Planck constant? Planck constant is wait. Here. Planck constant. Okay. 6.63 times to 10 to the minus 34. Okay. What else? M and E, right? What is M and what is E? M is the mass of electron, this one. 9.1 times 10 to the minus 31. And the E is what? Here. E is this one. 1.602 times to 10 to the minus 19.
B, C.
So this is equal to 4. 4 times pi,
A2.
pi, okay, times epsilon times this one, right? But I need to
Square.
divide by 2, divide by pi, then square, okay? Then what else? And then put it all together. Divide by n. Divide by e and square, right? So we can get. Okay. So this is meter. How do I convert meter to angstrom? Angstrom is 1 times 10 to the minus 10, right? Angstrom equal to 10 to the minus 10 meter, okay? So let's so equal to 0.53 angstrom. Okay, so we know what's the strength of the Bohr model. Bohr model can get this number 0.53 angstrom. By using the Schrödinger equation, we can also get this number. And we don't need to assume that they have an orbit. No. Using this equation, we can also get this number.
Okay.
Also, we need to get another one is the E1, because from our experiment, we know that the first ionization potential for hydrogen is this number. Can we get this one? Let's try. Try to get this. Okay. So, or we can start from here. Okay. Will be easier. So E1 equal to minus, okay, minus Planck constant square minus this one divide by 2 divide by pi. Planck constant divided by 2 pi is the h bar. Okay. Square. Okay. Divide by 2. Divide by n. This is n. Divide by this square. Okay. It's not 13.9. That's because EV 1 EV equal to 1.602 times 10 to the minus 19 joule. Okay, so we need to sorry, equal to this divided by this number. Okay, so it's 13.6 EV. So we don't need Bohr model. We use the Schrödinger equation. We can 100% replace Bohr model, and we can also get these two numbers.
Okay.
Right? And in this example, what quantum number we use? We only use n right? So if you use the 200, you can get another E2. 300, you can get E3. 400, you can get E4. And then finally, you can get E4 equal to E1 divided by 16. E3 equal to E1 divided by 9. This is also the result from the Bohr model, right? So that's why N, we call it principal quantum number, indicate energy. Okay, because once we know the N, we will know the energy for the electron in that orbit. So we call it principal quantum number. And what is L? What is L? Okay, so in this equation, remember, this is the equation we just used. We just used this equation, right? Okay. This equation, we call it R only function. R means only radius. Okay, so they have only radius. However, we call this number what? We call it orbit quantum number, right? So this is radius. This is orbit, right? We don't like orbit. Okay, so we need to make this 0, right? Because this is only R. This is only R. But if this is the momentum, orbital momentum, which means you have omega here, and or theta here, or phi here, but we don't like the theta. Okay, so what we can do is we can say, okay, if this is 0, then you disappear, right? You become an R only function. Okay, so let's put this together. And we can say all our energy, we can separate to, so that if there is a particle, electron here is something like here, okay? So I can separate the energy. I call this Ke radial. This is the Ke orbital. Right? So I can separate the energy to two directions. Okay? If I set this part equal to 0, if I set this part equal to 0, here is R only function, and this will become 0. Okay? So we know that Ke orbital should need to become h bar L times L plus 1 divided by 2n R squared. Okay, so we call this the orbital potential or orbital kinetic energy. Okay, this will be very important to what? To MRI. Okay, why we can see the MRI signal. Okay, why they are different? Because of this. Okay, so later this hour we will say a lot about NR physics. Okay, so this is the reason. Okay, and what do we have? So why we have NR signal? That's because we have ML and L. Okay, so when we have n equal to 1, 2, 3, 4, 5, L can only from 0, positive, negative 1, positive, negative 2 to L. L equal to 0, 1, 2 until n minus 1. Okay, that's why in this table, when n equal to 1, L can be only 0, because L equal to 0 to n minus 1. N is 1, 1 minus 1 is 0. So when n equal to 1, L can only be 0. For n equal to 2, L can be 0 and 1. Right, 0 and 1, because n minus 1, 2 minus 1 is 1. Okay, when n equal to 0, ml is 0. When n equal to 1, ml can be 0, positive 1 and the negative 1. Okay. So now we are going to talk about what is L and ml. So this is uppercase L. We define it equal to lowercase l times L plus 1 times square and the h bar. Okay, this is we call it angular momentum state. So have you ever heard about the orbit, 1s orbit, 2p orbit, d orbit? So s means L equal to 0, we call it s orbit. L equal to 1, we call it p orbit. L equal to 2, we call it d orbit. Okay? So if we see the periodic table, okay, right? This is s orbit. Okay, s orbit. N equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6. Okay, and n equal to 2, we have L orbit. P, SP, we have P orbit, right? This is L equal to 1. This is L equal to 0, right? L equal to 1 and L equal to 2. Okay, this is the L. And if n equal to 1, we have L equal to 0, then it's S orbit. N equal to 2, we have L equal to P orbit. N equal to 3, we have D orbit. N equal to 4, we have F orbit, then GH. Okay, so why don't we take a break and then come back in 10, 12. Okay? 10 minutes later. Then you can ask me question till now. Okay?